Hello, welcome back. We're looking at Big Idea 2. In Big Idea 2, it's all about bond energies, why things go together, why things exist at certain states of matter, gases, figuring out using all the gas laws, moles, solutions, moles, pressures, volumes, temperatures, how those are all related to each other. Solutions, how the number of solutes and the amount of solution and concentration and all those kinds of things are in Big Idea 2. And so Big Idea 2 is all about bonding and what that bonding does to sort of create and cause all the things around us. So here's an example of something you might see on the AP exam and some kind of questions that they might spring off of something like this. Now, this is a chart right here showing 3 different gases in a container. Now, this chart actually isn't showing these gases in a closed container. It's not supposed to, but I'm going to pretend that it is. So here's the idea. Let's pretend that this is a 1-liter closed container, right? We have 3 gases, diethyl ether, ethanol, and water. And so say that we're going to raise the temperature in that, and then this is the pressure in torrs over here on the side. All right, so first of all, some observations. What if you were to ask, what they were to ask you, given this situation, these 3 different gases in this solution, which one has the greatest density? Well, in this particular situation, you can see that diethyl ether is creating a lot higher pressure than both ethanol and water. And so therefore, what we can assume is that diethyl ether has the greatest density, or the greatest density of gases within here. It would be diethyl ether. But if you were to ask in between the 3 of these, which is the densest gas, and so then you'd just be looking for the one with the greatest molecular weight, which is also diethyl ether. Diethyl ether has a molecular weight of 74.12. Ethanol has a molecular weight of 46.07, and water is going to be 18. And what if you were to be asked in this situation, which one has the greatest kinetic energy? So in this particular situation, kinetic energy is, if this is a closed container, kinetic energy is related to temperature. And so what we're saying is that all of these gases were in this, and they were all at the same temperature at the same time. So actually they all would assume the same kinetic energy, right? So temperature and kinetic energy is so this is the average kinetic energy is equal at the temperature. So when we're saying temperature, what we're describing is the kinetic energy of all the gases in there at the same time. Now, if you were talking about molecular speed, though, that would be different. So kinetic energy is based off of both the mass and the velocity of each of these particles, but speed is just going to be how fast they're going. So if we're looking at these, which one of these are going to be going the same, or the fastest speed? Well, that's going to be the water, right? The water has got the smallest weight, therefore it's going to be going the fastest. So water is definitely the fastest. What if you were asked which one is going to make the most collisions, right, on the container wall? Well, collisions are going to be related to the one that's moving the fastest, so that's also going to be water. So because water is moving around there at a greater speed than the other one, it's going to bang into the walls the fastest. And then diethyl ether the least, because it's got more mass. It's 74. So remember, kinetic energy is mass and speed. So when you multiply mass and speed together, they're all going to be the same. Right? But if this is 18 and that's 74 times something, whatever else this is multiplied by compared to this is going to be a lot bigger. So this particular water molecules are going to be moving the fastest and causing the greatest collisions on the container. What about concentration? Well, when we look at this chart right here, we see that the diethyl ether is creating the greatest pressure, which means that it has a higher number of moles, because all of these gases, if they had the same number of moles, would be giving off actually the same pressure at the same temperature. And so they're not, and because they're not, we can assume that there's different number of moles for each of these gases that are in this container. So say that they had the same molar amounts. Well, in that case, all their concentrations would be the same, because the same molar amounts, right? And then the pressures would actually be the same. So in this particular case, which one has the highest concentration? Looks like diethyl ether, then ethanol, and then water. What if you were asked which one which one will deviate? Sometimes they talk about this, and we talked about ideal gases. Which one will deviate from ideal gas? All right. So whenever they ask questions like that, you're looking for the one that is going to exhibit polarity, right? Because in order to be an ideal gas, you have to have no attraction whatsoever, or no possible attraction for any other water or any other molecule in the situation. And so water is very polar. And so because water is very polar, the likelihood that water might try to connect to another water molecule is actually pretty high. So which one of these three is going to deviate from ideal gas? Well, water is going to be the first one to do that. So ideal gases assumes no intermolecular attractions at all. It assumes that they're totally separate from each other. And ethanol is an interesting one. It's going to exhibit mostly non-polar. Well, it's going to exhibit actually polar characteristics and non-polar. So ethanol is going to have the ability to be attracted to one another too. So this would be the next that would deviate. And diethyl ether is fairly non-polar entirely. So that one is going to be the least deviant from ideal behavior. All right, so let's think about some other things here. What if I was to ask you at 20 degrees, what is the total pressure in the canister? Well, then you would use Dalton's law. And so the P total would equal what? The P total would equal all these together. So here we've got about 20 is the pressure here. The pressure for ethanol is about 50. And the pressure for diethyl ether is about 480. So we'd add those all up. 20 plus 50, plus 480 would give us a grand total of 550 degrees. So remember that in any sort of situation where you have gases, the total pressure is just the addition of all the partial pressures inside. Now, what if I was to ask you how many moles? Could you solve for the actual amount of moles from a table like this? Let's say moles of ethanol. What's the moles of ethanol? Oh, well, anyway, sorry about my handwriting there. Moles of ethanol. Oh, I can't stand it. I'm going to have to fix that. There we go. That's a lot better, isn't it? Moles of ethanol equals what? Well, at 20 degrees Celsius, let's say the moles of ethanol well, let's just use this 20 right here. At 20 degrees, we figured out that the pressure was 50, right? And this is in torrs. So 20 degrees Celsius is going to be 293 degrees Kelvin. Very important when you use these gas laws to convert to Kelvin. Well, the ideal gas law assumes ideal conditions. So let's just use that. So the pressure here is going to be 50 torr, right? And the volume we said was 1 liter in this canister, equals number of moles. The R value for torrs is 62.4, and we have a 293 temperature, so that's going to give us exactly 0.003 moles. All right. And is that going to be different than water? Yeah, because water has a different pressure. And is that going to be different from diethyl ether? Yeah, because diethyl ether has a different pressure. So remember that if they're the same number of moles, they'll have the same pressure. But if they have different pressures, they have different number of moles, or if they have different number of moles, you'll know that they're going to exert different pressures, because the amount of them is going to be causing pressure, because pressure is caused by them impacting the sides. Now, we said that water is going to have the most collisions, but water is little. So its net pressure is actually going to be the force caused by its collisions. So in order to get the amount of collisions to actually get the right force, it has to go faster. So even though there's more collisions with the water molecule, it's not going to change the fact that its pressure is the lowest. Okay, so because water has the least amount of moles in this situation, its pressure is going to be the lowest. What if they asked you something like speed ratio? What's the speed ratio between diethyl ether and ethanol? And so speed ratio would be kind of the idea of, which one, we talked about how these have different molecular speeds based off their molecular size, and the water one's going to go the fastest because it's the smallest, and then ethanol, and then diethyl ether. So what is the actual speed ratio? Well, to do that, we'd use Graham's law for a fusion. And the idea with the fusion is the rate at which the gases were to escape if you were to open a small opening in the container. Well, if you open a small opening in the container, they're going to only escape as fast as these molecules impact that area, right? And so water's going to hit more often, so the water molecules are going to escape the fastest, and then ethanol, and then diethyl ether. So we can use Graham's law. And so let me just write Graham's law. So we could use Graham's law up here in order to solve a problem about speed. So let's see, Graham's, let's see, how do you spell Graham's? I think that's right. So if it's not, who cares? Graham's law is going to equal the velocity of the first gas over the velocity of the second gas is going to, and so what changes the velocity, or what changes the molecular speed? The bigness of it, right? So the bigger, the bulkier is going to go slower. And so it's actually going to be the square root of the molecular weight of the inverse of these two. So I would do molecular weight of 2 divided by the molecular weight of 1. So all you have to know is the molecular weight to figure out the ratio of speed of one to the other. So what is the ratio of speed of ethanol to diethyl ether? Well, let's go ahead and do that. So the velocity of ethanol, that says ethyl, sorry, you know what I mean, to the velocity of diethyl ether is, sorry about that, kids, equal to, so the square root of their molecular weight. So their molecular weights, and we got to flip these. So I want to put the second one on top here, and the first one. So diethyl ether is 74.12. We said that up here. And then ethanol is 46.07. All right, so if I take the square root of those, I'm going to get 1.27 to 1. So the speed of ethanol to diethyl ether is 1.27 to 1. So essentially 1.27 ethanol molecules is going to get through that hole by the time 1 diethyl ether gets through that hole. So basically they're gonna be going through at the same time, but this one's going to get a third of itself out faster. So hopefully that explains far more than you ever wanted to know about gases and gases in containers and what they do and all of those things. But oftentimes on the AP exam, you're going to have charts like this, and they're going to ask you a zillion questions. So what I try to do is take a chart like this and show you all the different sorts of kind of ways we could go with it and answer questions based off of it. Hope it helps.